Hello and welcome to another episode of Effective JaRu, the series where we have a look at effective Java and try to port items over to idiomatic Rust. Item 20 is a very interesting one. I'm looking forward to handling it. Prefer class hierarchies to tagged classes. Oh ho. So first of all, in Rust you don't have inheritance, so you strictly speaking have no hierarchy of types, which I think is a good thing unless you have full compiler support for all the shortcomings that have been documented over and over in the book so far, right? All the issues, safety issues that can arise and all the difficulties. So here it says that you shouldn't do tagged classes because of the shortcomings. The shortcomings are primarily, okay, the switch is not exhaustive, so you could easily miss a case here. And the code is more cluttered than it has to. You have multiple constructors here. You have extra fields which are partially unused, so basically wasted space, right? And this is just due to the fact you basically are misusing the classes which can't do what you can do in Rust. And Rust tagged types are actually quite common. They come in the form, they're super common. They come in the form of enumerations, right? So let's implement the figure here as an enum and say, well, we have a rectangle which should have, what does it need? A width, which is a double for them, and a length. For me, it would be more like height, maybe. Width and height, which is an F64. And then we have a circle, which just has a radius. And that's it. So the cool thing is that we see a union here. So all we need is the space for two doubles, for two F64s, and not three doubles, right? And of course, an extra field, maybe 32-bit or something for the tag itself, because we need to, or internally Rust will keep track of what kind of variant we are looking at when dealing with figures. So that's very nice. This is standard Rust, and this is one way of doing it. You could also use tuples here. So if you have a square, you could also, if you like, define it like so. S64, this square now says, well, this is, the length of it, of both sides. It's a square after all, but unfortunately, this tuple here, it doesn't, we could also do this, but this tuple doesn't explain what it is, so it's actually much better to use the length here of a side if you wanted that. So let's, why not? Let's do it. Let's do it like this. Maybe put it here. And again, this will still just be basically two doubles plus a little extra for the tag, which is still quite space efficient. So if we now wanted to implement something here, by the way, there's no need to do anything here. We might want to do this, make this public just to allow access. Oh, interesting. So we don't have to do this because these are public by default. Ah, interesting side effect, though. True. This is the only kind of constructor that you have, and these are public, right? So that's something to note. If you're happy with having your fields exposed, you can do it that way. But it's still very common in Rust, especially if you don't have to impose any invariants on the fields themselves, right? So if you want to implement the figure here, then we only have to implement one thing, which is area. And we take an immutable borrow here and return an F64, I guess. So now we can just match on ourselves and say if it's self rectangle, now we destructure it and say width is W and height is H. Then, okay, we can't do that with self, was an attempt. So we have to do figure like this, or use figure everything. So now we would be able to do that here, which is, I think, nicer. So let's do that. Yeah, I'm not sure if we need anything, so we do this by that, and we are done. What else do we have? Sure, comma, get the syntax right. We have a square, which just provides us with a length L. And here we do an L by L. And finally we have a circle with a radius. Oh, by the way, we don't have to do a remapping. I think this should work as well. Let's see. So radius by radius times pi. F64 pi maybe? Use std F64 pi? I hope that exists. Times pi. Yeah, technically, I think it makes no difference if we multiply the radius by the radius first, right? It should be the same thing. No, maybe it doesn't. I don't know. No, probably it doesn't. No. So that should be done like that. And we are exhaustive already, so there's no need to worry about anything. Oh, look at that. That doesn't work. There is no pi. Where do we get pi from? I've never used that. Where are the math constants here? Consts pi. See, makes sense. There's a submodule. And this is something we did in the previous session, right? We had a look at how you would do that kind of stuff in Rust, and this is exactly how it's done. You just have a module there that carries all the constants here. And that's how you would implement it in Rust. It's super clean, it's efficient, it's safe, it's fast. The compiler will do all the checking for you. And tagged types, they're not bad at all if you have support by the language. They're actually a good thing. And obviously we can still have a trait that says we can provide an area. So an area trait, which has an area function, taking an immutable cell, returning an F64. This is something you probably want to make generic so that the return type is not so hard-coded. But besides that, that's all we need to define it. And now we can implement this trait and then use the figure that we have even more generically. So if we want to implement area for figure, well, considering that, we can just do it like this, and we are good, right? So now people can generically use anything that supports an area. So means we could also have a struct here, struct foo figure, which is actually nothing, but we implement area for foo figure, and then say, well, the foo figure is kind of special, as it will return. Oh, excuse me. As it will return 42, and we are done. And now, when testing this, how would that work? We could have a function that actually returns the area generically. By having a type t that is supposed to implement area, and then we can compute the area on any item that supports t and return F64. So all we have to do here is t area, and we are done, right? So that is a generic form. Let's call it monomorphic area, because that will decide at compile time how to do that. And of course we have a polymorphic area that will determine at runtime what to do. And that totally works as well. We just have to specify that we want to have a borrow of an area here and return an F64. The code is exactly the same. Of course, it's not T here, but item, by the way. And that is it. And now we can have a few items here. yeah, what about for item in figure? Oh yeah, we should probably, oh no, wait, I'm not in a submodule here, so I don't have to do any import. Yeah, also this is not public here, so no one else could use this stuff. Let's make this pub as well, and this is maybe just for our test case, huh? So let's have a mod tests that will be conditionally compiled. Yeah, we definitely have to fix the syntax here soon. So we can drop this here. And now we have to use super everything so that we get what we need. Struct foo. Yeah. That is cool. And now for each item in figure rectangle, now we can initialize it just like you would expect to initialize a structure: width 1, height 1. I think we have to do it like that. And the cool thing is this is a union. We can now drop in, this type here and have a static, an array of these items with a size known at compile time, right? So we don't have to put anything on the heap here. Figure, what do we have? Square with length being 1.0. And figure circle, yeah, let's make it 2 and 3 maybe. And then I actually also would like to drop in the desired area that we would expect. In this case, it's 6. So let's put in tuples here. So this is then 16, the square, literally, the square of 4. 16, and the circle with a radius of 5. Actually, I have no idea. 1 by 1 by pi. So I think if we do this, then we can just say it's going to be pi, provided that we import this. Use std f64 const pi. Thank you. Yeah, let's fix the syntax here. So that's going to be pi. We close this one. We open up our thing. So that item now is a tuple. We might want to destructure this into a reft item and a copied want area. And now we can basically just say assert equal item area is want area for once. And of course we can make the actual calls. Let's see if that compiles so far. And then we want to test our little monomorphic and polymorphic items here. Cargo test lib. Cool, that actually works. And now we can do the same thing with monomorphic area. The item is a borrow already, so there's no need for me to specify anything. So that is that. And the same goes for polymorphic area, even though the polymorphic one is technically slower as it has some virtual function called overhead, right? It goes through a function pointer table to do that stuff. So of course, all that wouldn't be fun. We can at all times try this for the foo. Let f be a foo figure. And now we can provide f here, a borrow, and say it's 42. This is 42. This is F. So that works as well, even though all of a sudden it's a different type, basically. It's a totally different type. So that should also work. No. The trait area is not implemented for the type figure. What? Excuse me. So monomorphic is what it doesn't like. Ah. No. True. So let's try. That's interesting. So the polymorphic one works. Ah, haha, sorry, my bad. Look at me here. I'm not taking a borrow of T, I wanted to own it. And of course, this is why it didn't work. I don't want to own this, my bad. So now it works totally fine. And we are done. So it's true, type T for him was a borrowed area, borrowed figure, and for a borrowed figure, the trait is not implemented, right? You could implement it for a borrowed figure, then this would have worked, but alternatively, you would obviously do it like that. You expect T to have that implemented, and then the rest will work fine. So that's quite, traits are super powerful, and you can implement traits for all combinations of types, no matter how complex they are, and that's totally awesome. And very, very powerful indeed. And as you can see, this is nice. This is not a bad thing at all. And if you have simple types like this, maybe even stuff that you just use internally, then you would obviously do it like that. This book is always written like, yeah, you want to have the most powerful framework ever that is public to the world and used by 1 million people. Sure, then probably you would be careful about the fields you expose. On the other hand, if you say, well, it's that easy, it's never going to change, then this is it, right? You always have ways to deprecate stuff and or to maybe have a version 2 of the entire library, and people who want to use it will port their code over. The others will be stuck with the old stuff. Yeah, so that is that. In Java, obviously, you would use or prefer a hierarchy here because indeed, this is not nice. This is error prone. I mean, it's absolutely true that in Java you wouldn't want to do this. Use a hierarchy instead. I would be tempted to agree here. So you have a figure, which is an abstract class which just defines an interface here. Considering what he said previously, that you probably want to prefer interfaces over abstract classes, I think he's breaking with his own ideas, because I would make this an interface. I would treat this like a trait and say, well, there's something that can build the area of something because that's more flexible, right? That's much more flexible. So areable or area item or something. And if you implement area item, then you can compute an area. And this is really the trait idea. I don't think that he is really aware of what's going on. I mean, I think thinking in class hierarchies all the time is a bad thing. You should think of capabilities and then say, well, capabilities are encapsulated in interfaces. So really what you want to do is implement interfaces here. So is there any kind of code that we can run? No, it just shows that now it's clean and separated, and that's all good and nice. But really, I would call this, I'll keep the name here, but I will call it public interface. And then let's see if we can still build stuff. Let's try the circle here. Build current class shouldn't work because no interface expected here. We have to say implements figure. Oh, and now this should work, right? Attempting to assign weaker access privileges was public. Oh, true. Interesting. We don't want that. So like this, huh? So now it works, cool. And this is how I would do it. This is much more flexible. Don't impose a hierarchy. Don't use abstract classes unless it's in order to have a default implementation for the bulk of interface methods that one would otherwise have to implement. Really, this is what I get. This is how I would behave in Java, just to make it easier on you. All this inheritance stuff, really, it leads to taxonomies which are inflexible and which bite you at some point. So yeah, I guess we have to fix the other ones as well, just to fix the book in a way, a little bit at least. Implements figure, yeah, that must be public. That should now work. Thank you. Same with square. Implements this. Oh no, that truly extends rectangle. Sorry. That's fine now. That should be cool. And yeah, that's how I see it. Use interfaces, stick to your word, dear author, and don't kind of force people into hierarchies that actually are more flexible. If you just say, well, let's have something that can compute the area, and we are good. Let's keep things slim and nice. On the other hand, I think the problem is that you can't really define that you want combinations of that stuff. So if I have a function that supports area, or if I have something that needs something that supports an area and a volume, for instance, a surface area and a volume, then I can easily specify this with at least in monomorphic situations in Rust, where something like that wouldn't exist. Well, okay, there's no monomorphism really in Java. Not so much, at least. So yeah, that's understandable. Yeah, basically, you will need an interface that kind of inherits or extends the interfaces that you actually seek to define what you require. That's also okay, by the way. This is also something you would obviously do in Rust in order to get one virtual function pointer that can access multiple traits at once, right? That's how you would do it. Probably I should show this. How much time? Yeah, let's say we have a volume here, which makes no sense for two-dimensional items. But if we wanted to have a trait volume that has a function volume returning an F64, then we could now specify that we would like to have usage 2, actually test usage 2. Yeah, we could now specify a function in the monomorphic field that says, well, fn monomorphic computation that wants a t, where t is area and volume. And now we can just say, well, we take an item t and produce this. And then you can do this. And you can say, well, area times item volume, and we are totally cool. Where something like this now doesn't work in the polymorphic area, right? Why does it not work? Well, we cannot do the plus thing here. Let's see if that compiles. That does compile, even though the function is never used. If we could, yeah, right now we don't compute. We could implement this for foo figure. Impl volume for foo figure, because it's returning the volume, of course, we want to return. F64, F65, there we go. And then we say just 42 times 42 times 42. That's our volume here. And now if you would try the monomorphic computation with a figure circle with a radius of 1 whatever, then you would see at compile time that this doesn't suffice for what we need. First of all, we need a borrow. Second of all, the trait volume is not implemented for the type figure. However, if we do that for our foo figure, then this will be totally fine. As you can see, the polymorphic one we cannot use. Not that easily, at least. Polymorphic computation. Because here we cannot say that our item should be an area plus a volume. This doesn't work. Right, so we want to do the same thing actually. Let's just do it. And this will now nicely fail on us. Yeah, so what we need is a trait that basically requires both traits to be present. We can do this and say, well, trait area volume requires area and volume. And this is an empty trait. It really just says we need both of these combined, and then we can specify this, and this will be totally fine. Let's try to use it, because then it will not be totally fine, as our foo figure here doesn't actually implement that trait yet. See, area volume is not implemented. The cool thing is all we have to do is to, well, implement it. So area volume for foo figure, which is an empty one as well. Foo figure already implements everything it needs to implement. And now this works. This really just creates a function table that contains all the functions combined of volume and area. And I do wonder what would happen if you would also specify an area here and implement it in terms of volume. This makes no sense, but this also would create a clash, right? So what happens if there is a clash? So here you see that we can easily pre-implement this. So that's a provided method, whereas this is a required method. And now we should have some sort of name clash, right? Multiple applicable items in scope. Cool, so that's totally true, that's good. So we cannot screw this up without the compiler telling us, even without using override annotations and this and that, you know, just standard. Just part of sanity, I think. Yeah, so that is that. I totally dig it. I like it. Tag types are absolutely fine and are very common in the Rust world, whereas I do agree that in Java you probably do not use them. Instead prefer interfaces, you know, and then implement the concrete type as you like it and keep it slim and nice. I mean, an instance in Java is never slim, thinking about it, but you know, do it as good as possible in Java. How could Java ever become that big? I don't get it. I mean, as it stands right now, I would totally prefer using Go, because Go is easier, cleaner, and not slower than Java. You know, Go is much slower than Rust, but if it's really just about that, then, you know, the performance is equivalent, I think. And it doesn't have any safety mechanisms either, so less safety, but it, you know, but considering that even in Go you can't do any constness, you know, everything is always writable, and that in Go at least you are aware of the fact that you're dealing with pointers that you possibly have to check for null, which even here is hidden, you know, you just think it's an object, but it is actually a reference to an object that can be null. Then I would prefer Go, totally. No doubt about that. But anyway, that should be the session for item 20. Thanks for watching and have a great day.